Good morning, everyone. Now, the part 4 of the lesson thermodynamic is heat. Heat is our next topic. So, uh, temperature is the measure of degree of hotness or coldness. If we want to find the definition of the temperature, so the temperature is the measure temperature is the measure of degree of hotness or coldness. Temperature is the measure of degree of hotness or coldness and the quantity of energy which flows between system and surrounding on account of temperature difference is called heat So temperature is the measure of degree of hotness or coldness and the quantity of energy which flows which flows between the system and the surrounding on account of temperature difference is called heat. Now, heat is designated by the letter Q and it is a path function. Means it depends upon the path followed. So the Q is positive. The Q means heat is positive when heat is transferred from the surrounding to system. The heat is positive when heat is transferred from surrounding to system, and Q is negative. The value of Q is negative when heat is transferred from the system to the surrounding. Q is positive. The value of Q is positive when the heat is transferred from surrounding to system, and when the heat is transferred from system to surrounding, then at that time the value of Q will be negative. So if the change in temperature is delta T. Here the meaning of delta is change. So if the change in temperature is delta T, then heat transferred, that is Q is equal to coefficient multiply delta T. This is the formula. So the magnitude of the coefficient depend upon the size, it depend upon the composition and the nature of the system So we have this formula. Now, the next topic is heat capacity. This is our next heading. This is the heat capacity. In the expression of heat, that is Q is equal to coefficient multiply delta T. If coefficient is C, let us consider, if coefficient is C, capital C, if coefficient is C, then Q is equal to, in place of coefficient we can write C, and that is delta T. Now here the meaning of C is the coefficient, that is C is the coefficient, and this coefficient, that is C, we are talking about the C, we are talking about the coefficient. This coefficient C is called, this is called heat capacity, and this coefficient C is called heat capacity and is defined as, and this C is defined as the quantity, this C is defined as the quantity of heat required to raise the temperature. Heat capacity, C is the heat capacity, coefficient is also termed as the heat capacity and is defined as the quantity of heat required. This C is the quantity of heat required to raise the temperature of a system, to raise the temperature of a system by 1 degree. This is the heat capacity. It is defined as, it is a quantity of heat. C is the quantity of heat which is required to raise the temperature of system, not surrounding, system, by 1 degree. That is called the heat capacity. And if the magnitude of heat capacity is large, then there is a small rise in a temperature by a given amount of heat. For example, heat capacity of water is large. Heat capacity of water is large. Therefore, the large amount of heat is required to raise the temperature. So, water is the best example. H2O, the heat capacity of water, heat capacity, that is C of H2O is large. The heat capacity of water is large, and therefore a large amount of heat is required. Large amount of heat is required to raise its temperature. Because heat capacity is large, therefore a large amount of heat is required to raise its temperature. Or in a chemical calculation, we often use the specific heat capacity and the molar heat capacities. In chemical calculation, there are two more terms. We use two more terms. One is the specific heat capacity and another one is the molar heat capacity. Now, specific heat is defined as the heat required to raise the temperature of 1 unit mass by 1 degree. By 1 degree, either in the Celsius or either in the Kelvin. And when the definition is given in terms of a mole, when we are using the term mole, so it is considered as molar heat capacity. when definition is given in terms of mole, so for that time we use the term molar heat capacity. That is the heat capacity of mole. That is how much mole? 1 mole. The heat capacity of 1 mole of a substance. So the specific heat capacity, there are two terms. One is the specific heat capacity. So the term specific heat capacity, it is designated by C, that is small c. Specific heat capacity is designated by small c, and we have a formula for that. That is Q is equal to C multiply M multiply delta T. This is the formula. So where Q is, what is Q? Q is the heat required. Q is the heat required to raise the temperature by 1 degree Celsius. Heat required to raise the temperature by 1 degree Celsius. Okay. Now, next is the C. C is specific heat capacity. C is the specific heat capacity. And what is delta T? This is change in temperature. Delta T is change in temperature. So by the help of this definition, we can easily elaborate the heat capacity or the specific heat capacity. Now the next topic is heat capacity at constant volume. Heat capacity at constant volume, that is CV. Here the V stand for the volume. The term V stand for the volume and C is for the heat capacity. So it is defined as the heat capacity at constant volume is defined as the amount of heat required to raise the temperature of 1 mole of a gas. The amount of heat which is required to raise the temperature of 1 mole of gas by 1 degree. By 1 degree when we have a limitation. When volume of the gas is kept constant. When volume of the gas is kept constant. Here the volume is constant. So that amount of heat is known as heat capacity at constant volume. Now the next term is heat capacity at constant pressure. That is CP. Heat capacity at constant pressure. Now here it is clear from the name that pressure will be constant. So it is defined as the amount of heat. It is the amount of heat which is required to raise the temperature of 1 mole of a gas by 1 degree. And what will be the condition? When pressure of the gas is constant. When the pressure of the gas is constant. Here in this case, the volume is constant, and here in this case, when we have used the term constant pressure, so here the pressure will be constant. So the heat capacity at a constant pressure is the amount of heat which is required to raise the temperature of 1 mole of a gas by how much degree? By 1 degree, when pressure of the gas is constant. The condition is the pressure of the gas is constant. So therefore Cp, that is constant pressure or heat capacity at constant pressure, is the heat required for the purpose of, Cp is the heat. It is the amount of heat which is required for the purpose of the first one is increasing temperature of 1 mole of gas, increasing temperature of 1 mole of gas through 1 degree. And the second one is for increasing the volume, for increasing the volume of the gas, against volume of the gas against external pressure. Volume of the gas against external pressure. So for these two purpose, the heat capacity at constant pressure is required. First is the increasing temperature of 1 mole of gas, increasing temperature of 1 mole of gas through 1 degree, and the second one is for increasing the volume of a gas against external pressure. So the Cp and the Cv. Cp, this is the Cp and this one is the Cv. So Cp and the Cv are related to each other. Cp, that is constant at heat capacity at constant pressure, and the heat capacity at constant volume are related to each other. They both are related to each other by the expression, that is Cp minus Cv is equal to Nr. So this is the relation between the Cp and the Cv, and its derivation is given later in this chapter. We have derived this later on. So heat capacity at constant pressure, Cp, is always greater than this one, So the heat capacity at constant pressure is always greater than the heat capacity at the constant volume. So we can also write it as that is Cp. The value of the Cp is always greater than the value of Cv. So now we have the two statements. The first one is Cp minus Cv is equal to Nr. This one is the Nr. R is the universal gas constant. This is the number of mole, and Cp is the heat capacity at constant pressure, and Cv is the heat capacity at constant. One statement is Cp, and this is the verified statement that the Cp should be always greater than Cv.